Now let's do one example. What we have here is a steam turbine at a steady state. We know P1 is 5 bar, T1 is 320 Celsius, P2 is 1 bar, and T2 is 160 Celsius. Volume flow rate at number 1 is Q1 equal to 0.65 cubic meter per second. And we know we use Q for both heat transfer and volume flow rate. And from the unit cubic meter per second, we can tell this Q is volume flow rate instead of heat transfer. And just like before, we always use a diverging duct for turbine because what happens in a turbine is an expansion process. So now that's why you can see the pressure goes down from 5 bar to 1 bar because this is an expansion process. Okay, what we want to find is first of all sketch 1 to 2 and 1 to 2s on a T versus S diagram. 1 to 2 is reality while 1 to 2s is isentropic, meaning everything's perfect and is ideal. Second part is to look for W dot T, the power generated by the turbine. And part 3 is to look for sigma dot T, the entropy production rate by the turbine. And number 4 is to look for eta T, efficiency of the turbine. Okay, so now let's start from part 1. First of all, let's sketch a T versus S diagram. Okay, and first one, we sketch vapor dome. And on the vapor dome, we have constant pressure lines. Let's sketch two of them, one for P1, the other one for P2. So this one must be P1, the bottom one must be P2, because P1 is higher, P1 is 5 bar, P2 is 1 bar, so P1 must be on top because of the rule, which is the higher this line is, the higher the pressure it represents. Okay, so now what we're going to do is to locate point number 1. And again, when you locate a point, essentially you're asking yourself, what is the phase of this point? So what is the phase of point 1? Take a look. We know P1, 5 bar. We know T1, 320 Celsius. How do you fix the state of number 1? We've done this several times now. You go to table A3, you start from pressure 5 bar, you look for the corresponding saturated temperature, and compare that with your actual temperature T1. If your actual temperature T1 is greater than saturated temperature, then your point number 1 must be superheated. So let's go to table A3. We start from pressure P1, which is 5 bar. And from the table, we look for the corresponding saturated temperature. We call it Tsat1. And the solution is 151.9 from the table. Unit is Celsius. And our actual temperature T1 is 320 Celsius, which is even higher than the saturated temperature. So the conclusion is point 1 must be superheated. Okay, is that enough for us to fix point number 1? Let's take a look. If I put point number 1 here, does this satisfy the requirement to be superheated? Yes. And if I put point number 1 here, how do you sketch 1 to 2s? And from before we know 1 to 2s, isentropic, meaning entropy does not change. So when you sketch this process, the x coordinate doesn't change. So 1 to 2s will be a vertical line on a T versus S diagram. So that means if you sketch 1 to 2s, it must be a vertical line. So case number 1, 1 to 2s, go straight down. And number 2s in this case will be a mixture because it is within the dome. Option number 2, can I put number 0.1 here so that when you go straight down, number 2s will be G point. Does it satisfy the requirement for point number 1 to be superheated? It does. Or can I put number 1 further to the right here? And then when I sketch 1 to 2s, go straight down. If that's the case, point number 2s will be superheated. So actually I have three possible solutions actually. The three possible solutions are, first one, point 2s to be a mixture. Second solution, point 2s to be G point. Third solution, point 2s to be superheated. So we need to find which one is the correct one. So what we need to do is delete this line and delete this one. Okay, let me just sketch this diagram again. Okay, so usually what we do is we find a reference line. And this is my reference line across this G point. So what is the x-coordinate of this point? The x-coordinate is S2G. S2G, 2 means at P2, G means saturated vapor. So that's my reference point. And then what you do is to look for S1. If S1 is less than S2G, then point 1 must be to the left of this reference line. If S1 is equal to S2G, then point 1 must be right on this line. If S1 is greater than S2G, that means you must put number 1 to the right side of the reference line. So from doing that, we can fix the location of point number 1. Okay, so what we just need to find is S1 and S2G. Okay, so now how do we look for S1? What's the first thing you need to do? You need to find out the phase of number 1. What is the phase of number 1? Superheated. So if you're looking for a property for superheated water vapor, you have to go to table A4. When you go to table A4, you have to have two inputs. One of them has to be pressure. So we actually know P1, which is 5 bar. The second input we have is temperature, T1, 320 Celsius. And from table A4, you can easily find S1. S1 is 7.5308 kilojoule per kilogram per Kelvin. So now I have S1. Alright, since I am at the table, I might as well write down other properties. So if, for example, I also write down H1, which is 3105.6 kilojoule per kilogram. And then we also write down new one, specific volume from the table, which is 0.5416 cubic meter per kilogram. Okay, so those are the three properties we look for from the table. We just found S1, and S1 is the one I'm looking for at this moment. Okay, so now next we're looking for S2G. How do we look for S2G? We need to first find out what's the phase of point 2G. Obviously, the phase of point 2G is this point. This point is point 2G. Okay, let's give this point a name. The phase is saturated vapor. So now what do we know about point 2G? Because if we know the temperature of point 2G, we can go to table A2. And if we know the pressure of point 2G, we can go to table A3. What do we know about point 2G? Point 2G is on which line? Point 2G is on P2 line. So that means the pressure of point 2G must be equal to P2. And we do have P2. P2 is given as 1 bar. So from the table, we can easily find S2G. You just go to the table and you look for a column SG. Okay, S2G is 7.3594 kilojoule per kilogram per Kelvin. So now I have S1 and my reference S2G. Which one is actually bigger? S1 is actually bigger. S1 is bigger than S2G. So that means 0.1 . 0.1 . must be to the right of point 2G. So now we go back to our diagram, and we know point 1 must be on P1 line, but also it has to be on the right side of point 2G, which is to the right side of this dashed line. So point 1 must be somewhere here. Okay, so now I have located the position of number 1. In the beginning, we said point 1 has 3 possible locations. First one, to the left of this dashed line. Number 2, right on this dashed line. And number 3, to the right of the dashed line. Now we've found the correct one. It has to be to the right of the dashed line by looking for S1 and S2G. Okay, so now we're done with S1, locating point number 1. How do we locate point 2S? 1 to 2s is isentropic, so it has to be a vertical line. So 1 to 2s is very straightforward. You just draw a vertical line and go straight down, and that will be your point 2s. Okay, point 2s, vertical line, go straight down. So that's point 2s. So now we've done point 1 to 2s. Next, let's sketch process 1 to 2. How do we sketch 1 to 2? Remember 1 to 2. 1 to 2 is reality. If it is reality, what's going to happen? Delta S will always be greater than 0, meaning S2 will always be greater than S1. So 1 to 2 will always be skewed to the right. Okay, 1 to 2 skewed to the right. There's only one possible solution. Number 2 has to be superheated. So that's 1 to 2. Skewed to the right, number 2 has to be superheated. And that's the only possible solution. So that is the diagram. Okay, 1 to 2 to the right. Because it's reality, it has to go to the right. So point 2 must be superheated. Okay, so that's part 1, the diagram. And then part 2. Part 2 is to look for W dot turbine. Okay, you start from first law. If you look for work, you start from first law. And obviously the long version. Okay, which we just did already from last time. So if you can remember, the solution was W dot turbine over M dot is equal to H1 minus H2. This comes from first law. Okay, so now we're looking for W dot of the turbine. So the equation becomes M dot times H1 minus H2. Okay, so next one. We don't have mass flow rate, we do have volume flow rate. Let's recall. Mass flow rate is equal to volume flow rate multiplied by density. So now I can rewrite mass flow rate into Q dot 1 multiplied by rho 1. You can apply this equation to any surface. For example, you can write Q dot 2 multiplied by rho 2. It doesn't matter. The reason why I choose to use surface number 1 is because we know Q dot 1. Okay, H1 minus H2. And next, we don't usually use density. What do we use in this class? We use the inverse of the density. The inverse of the density is equal to nu, specific volume. So this equation becomes Q dot 1 divided by nu 1 times H1 minus H2. Let's take a look. Do we have Q dot 1? Yes, volume flow rate Q dot 1 is given. Do we have a nu 1? Yes, we do. We found nu 1 earlier. Yes. Do we have H1? Yes, we do. We found H1 earlier, right here. Do we have H2? Not at this moment, so we just need to find H2. How do we look for H2? If you're looking for a property, the first thing you need to do is to identify the face of this point. What's the face of point number 2? Let's take a look at the diagram. Number 2 is to the right side of the vapor dome, so it is superheated. If you are looking for the property of a superheated water vapor, then you have to go to table A4. When you use table A4, you have to use two inputs. Do we know two things about number 2? Yes. First of all, we know the pressure, P2 is 1 bar. And next, we know the temperature of point 2. T2 is 160 Celsius given. And from the table, you can easily find H2. H2 is 2796.2 kilojoule per kilogram. And I also write down S2, even though I'm not looking for S2 at this moment. It's 7.6597 kilojoule per kilogram per Kelvin. Okay, so now let's go back to the equation. Do I have everything the right hand side now? Yes, I do. So W dot turbine can be calculated from Q dot 1 over nu 1 times H1 minus H2. Let's plug in the numbers. Volume flow rate Q dot 1 is given as 0.65 cubic meter per second SI unit. Divided by nu 1 is 0.5416 cubic meter per kilogram SI unit. Multiplied by H1, 3105.6 kilojoule per kilogram. So we convert it to joule per kilogram by multiplying 1000 minus 2796.2 kilojoule per kilogram. Again, multiply by 1000 to convert kilojoule to joule. So the final solution for W dot T is 371.6 times 10 to the third. The unit must be SI. The SI unit for W dot, which is power, is watts. And then one more step, 371.6 kilowatts. The solution is positive, which makes sense because the turbine generates work. If the turbine generates work, the solution must be positive. So this is part 2, how to look for work. You can find it from first law of thermodynamics. Okay, so now we're done with part 1 and part 2. Let's move on to part 3. Part 3 is to look for entropy production rate for this turbine, sigma dot with the subscript T, meaning turbine. Which equation has actually sigma dot in it? There's only one, that is entropy rate balance equation for a control volume, derivative capital S over dt equal to sigma j from 1 to n q dot j over tbj plus sigma m dot I si minus sigma m dot e se plus sigma dot add a subscript T, meaning turbine. Okay, so now let's simplify this equation. First of all, the system is at steady state. Left-hand side goes to 0. And 122 is reality. What is reality? If you forgot, let's go back. 122 is reality. Reality means here, adiabatic and irreversible. So we still have adiabatic. If it's adiabatic, that means there's no heat transfer. If there's no heat transfer, then Q must be 0. That's why we can get rid of the first term in the right-hand side. The reason is adiabatic. Okay, so this equation becomes 0 equal to 0 plus, we only have one inlet, so it's m dot s1 minus only one outlet, so m dot s2, and plus sigma dot turbine. I didn't give m dot a subscript because the system is at steady state, so mass flow rate doesn't change. Because we're looking for sigma dot t, so move that term to the left-hand side alone. What is left is m dot times s2 minus s1. Do we have mass flow rate? Not directly. We can rewrite mass flow rate into volume flow rate, which is q dot 1 over nu 1, just like before. Multiplied by S2 minus S1. Do we have Q dot 1? Yes. Do we have nu 1? Yes. Do we have S2 and S1? Yes. Okay. I have S2 from the table right here, and I have S1 from the table right here. So now I have everything in the right hand side. Let's do plug and chug. Okay, Q dot 1 is 0.65 SI unit. Nu 1 is 0.5416 SI unit. multiplied by S2, 7.6597 kilojoule per kilogram per Kelvin. So multiply by 1000 to convert kilojoule to joule. Minus S1, which is 7.5308 kilojoule per kilogram per Kelvin. So again, multiply by 1000 to convert kilojoule to joule. Okay, so our final solution is 0.155 times 10 to the third, and our solution must have an SI unit. What is the SI unit? That is watt per Kelvin. Okay, watt per Kelvin. If you don't know the unit, you can also just calculate the unit. So for example, what is the unit for Q dot? That's volume flow rate. That's cubic meter per second. Divided by new one, what is the unit for new specific volume? Cubic meter per kilogram. Multiplied by what is the unit for entropy? After our conversion is joule per kilogram per Kelvin. So now what's going to happen? Cubic meter, they cancel. Kilogram, they cancel. So joules per second. What is joules per second? That becomes watts. And then watt divided by Kelvin. That's it. Watt per Kelvin. That is the unit that is left. Okay. Joules per second and then Kelvin. Joules per second is called watts. So that's why the unit is watt per second per Kelvin. Okay, so now maybe one more step. 0.155 kilowatts per Kelvin. And our solution is positive, which makes sense. If sigma is positive, that means your system is not reversible. It is irreversible, which is the case for everything in reality. So that's part 3, entropy production rate from entropy rate balance equation for a control volume. And then we go to part 4, the last part of this example. What is part 4? Part 4 is very straightforward, just to look for the efficiency of the turbine. Okay, so from last time we know the efficiency of a turbine has an equation that is H1 minus H2 over H1 minus H2S. Let's take a look. I have H1 and I have H2. I just don't have H2S. If I can find H2S, then the question is done. How do we look for H2S? The first question is, again, identify the phase of point 2S. Let's take a look. Go back to our diagram. And where is point 2S? Point 2S is to the right side of the vapor dome. So that means point 2S must be superheated. If it is superheated, then you have to go to table A4. When you go to table A4, you have to have two inputs. One of them has to be pressure. So what is the pressure of point 2S? We can see point 2S is on P2 line. So the pressure of point 2S must be equal to P2. And what is the second input we have about point 2S? You've noticed 1 to 2S is a vertical line, so they must have the same x coordinate, which means S1 must be equal to S2S. And do we have S1? Yes, right here. So that means we have S2S, which is the second input we have to use. So because it's superheated, we're going to use table A4. The two inputs. First one is the pressure. Pressure of point 2S is equal to P2, and that is 1 bar. The second input we have is S2S, and that is equal to S1, which is 7.5308 kilojoule per kilogram per Kelvin. And now from the table, you can look for H2S. Okay, so now we can show you the table. Table A4. The pressure we want is 1 bar, which is right here, 1 bar. Okay, what we have as the second input is S entropy. Entropy is the last column, so we go to the last column and look for our value, which is 7.5308. I don't have exactly this number, but our number is between those two. So the one I'm looking for is H, enthalpy. Enthalpy is in the second last column, so our enthalpy must be between those two numbers. And obviously we have to use interpolation. Okay. All right, interpolation, we have done it so many times, you can use either Excel or MATLAB, or just by hand. From interpolation, we know H2S is 2743 kilojoule per kilogram. So now I have everything in the right hand side. I can easily find turbine efficiency, eta T. H1 is 3105.6 minus H2, which is 2796.2. And do it again. Minus H2S, which is 2743. Okay, all four numbers have the same unit, which is kilojoule per kilogram. Even though they're not SI unit, it doesn't matter because they will cancel in the end. So our solution is 0.853 and it doesn't have a unit. So you can see the turbine efficiency is 85.3%. It's very, very high. It's very, very high. So how come when it comes to the whole vapor power system, like the power plant, usually the efficiency is only 40%, which is very, very low, even though the turbine itself has a very high efficiency. The turbine actually has a very high efficiency. The compressor also has a very high efficiency. The boiler is also high. The reason why the whole system has a relatively low efficiency is because of the condenser. Because what does the condenser do? The condenser does nothing but to lose energy, to lose heat. So that's why when it comes to the whole setup, the whole system, the efficiency is low, all because of the condenser. And the second law tells you you have to lose heat. Condenser has to be there. You can do nothing to change that.